Lesson: Recurrent neural networks in cyber defense. Recurrent neural networks have emerged as a powerful tool in the realm of cyber defense, offering innovative solutions to complex problems associated with cybersecurity. Unlike traditional neural networks, RNNs are designed to recognize patterns in sequences of data, making them particularly effective for analyzing time series data, such as network traffic logs and user behavior patterns. Their ability to maintain a memory of previous inputs enables them to detect anomalies and predict future events with a high degree of accuracy, thereby enhancing the capabilities of cybersecurity systems. One of the primary applications of RNNs in cyber defense is in the detection of network intrusions. Traditional methods of intrusion detection often rely on predefined signatures of known threats, which can be circumvented by sophisticated attackers employing novel techniques. RNNs, however, can learn to identify subtle patterns and correlations in network traffic that may indicate an intrusion, even if the specific attack vector has not been previously encountered. For example, a study by Kim et al. Demonstrated that RNNs could effectively detect distributed denial-of-service attacks by analyzing the temporal patterns of network traffic. By training the RNN on normal traffic patterns, the system was able to identify deviations that corresponded to DDoS attacks with high accuracy. Moreover, RNNs are instrumental in enhancing the capabilities of anomaly detection systems. Anomaly detection in cybersecurity involves identifying unusual patterns that do not conform to expected behavior, which is crucial for uncovering stealthy attacks that might evade signature-based detection methods. RNNs excel in this domain due to their proficiency in handling sequential data. A notable example is the work by Malhotra et al., where an LSTM-based RNN was used for time series anomaly detection. The model was trained on normal operational data and was able to detect anomalies by recognizing sequences that deviated significantly from the learned patterns. This approach is particularly useful in identifying advanced persistent threats, which often involve prolonged and covert activities. RNNs also enhance user behavior analytics, which is a critical component of modern cybersecurity strategies. UBA focuses on monitoring and analyzing user activities to identify potential insider threats or compromised accounts. Given the sequential nature of user actions, RNNs are well suited for this task. For instance, a study by Eberl et al. Utilized RNNs to model user behavior and detect anomalies that could indicate malicious activities. By learning the typical sequences of actions performed by users, the RNN could flag deviations that might suggest an insider threat or a compromised account. This proactive approach allows organizations to respond to potential threats before they can cause significant damage. The predictive capabilities of RNNs also make them valuable for anticipating future cyber threats. By analyzing historical data, RNNs can identify trends and patterns that may indicate emerging threats. For example, a study by Brown et al. Employed RNNs to predict the likelihood of different types of cyber attacks based on historical attack data. The model was able to forecast future attacks with a high degree of accuracy, providing valuable insights that could inform proactive defense measures. This ability to predict and prepare for potential threats is a significant advantage in the ever-evolving landscape of cybersecurity. In addition to their application in detecting and predicting cyber threats, RNNs can also be used to enhance the effectiveness of automated response systems. Automated response systems are designed to take immediate action when a threat is detected, mitigating the potential impact of the attack. RNNs can improve these systems by providing more accurate and context-aware responses. For instance, a study by Shaukat et al. Demonstrated the use of RNNs in an automated incident response system. The RNN was trained to classify different types of cyber attacks and recommend appropriate response actions based on the context of the attack. This approach not only improves the accuracy of the response, but also reduces the time required to mitigate the threat. Despite their many advantages, the implementation of RNNs in cyber defense also presents certain challenges. One of the primary challenges is the need for large amounts of labeled data to train the models effectively. In many cases, obtaining labeled data for training can be difficult, especially for rare or novel attack types. Techniques such as transfer learning and data augmentation can help address this issue by leveraging existing data to improve the performance of the RNN. Additionally, the complexity of RNN models can make them difficult to interpret, which is a significant concern in the context of cybersecurity, where understanding the reasoning behind a model's decision is critical. Research is ongoing to develop methods for improving the interpretability of RNNs, such as attention mechanisms and model-agnostic interpretability techniques. Another challenge is the computational resources required to train and deploy RNN models. Training RNNs can be computationally intensive, particularly for large-scale cybersecurity applications that involve analyzing vast amounts of data. Advances in hardware acceleration, such as the use of GPUs and TPUs, have made it more feasible to train complex RNN models, but resource constraints can still be a limiting factor for some organizations. Additionally, the deployment of RNN models in real-time cybersecurity systems requires efficient and scalable algorithms to ensure timely detection and response to threats. In conclusion, recurrent neural networks offer significant potential for enhancing cyber defense capabilities through their ability to recognize and learn from sequential data patterns. Their applications in intrusion detection, anomaly detection, user behavior analytics, threat prediction, and automated response systems demonstrate their versatility and effectiveness in addressing various cybersecurity challenges. While there are challenges associated with the implementation of RNNs, ongoing research and technological advancements continue to improve their performance and accessibility. By leveraging the power of RNNs, organizations can enhance their cybersecurity posture and better protect against the evolving threat landscape.